Well, hold on to your hats, get your seatbelts on, make sure your tray tables are in the upright position because today, there's a lot we're going to be looking at. Redox reactions. Oh, yeah. The word redox is an amalgamation of two words, a reduction, which refers to the gain of electrons, and oxidation, which refers to the loss of electrons. You were first introduced to this back in the electrons unit when we looked at how ions were formed, but now we're going to take a real deep dive into this whole idea. So there are three basic kinds of chemical reactions we're going to be looking at over the rest of this course. There's going to be redox reactions, which take place due to changes in charge. These include synthesis, where two elements combine to make a compound, decomposition, where a compound breaks up into its component elements, or at least simpler substances, and single replacement, where one element replaces another in a compound. The next topic we're going to do is ion exchange, which is the formation of an insoluble precipitate. This would include double replacement, which acid-base neutralization is a form of. And then at the very end of the course, you'll look at organic reactions. Combustion, which is burning, addition, substitution, etherification, esterification, saponification, fermentation, and polymerization. So all of those are coming up. So, some relevant vocabulary to help you get started for today. First of all, redox, again, is a combination of reduction and oxidation, which indicates a change where there is an exchange of electrons. Someone's losing them, someone's gaining them. Reduction is the gain of electrons, resulting in the charge becoming more negative. The word reduction is referring to what's happening to the charge. It's becoming more negative. Oxidation is the loss of electrons, and it was first described with respect to oxygen reacting with metals. The metals lost their electrons to oxygen, so it was called oxidation, resulting in the charge becoming more positive. And spectator ions are any ions whose charge does not change during the reaction. And by the way, the word species refers to things like atoms or ions, whether monatomic or polyatomic. So, anybody here mow their lawn? Why do you mow your lawn? Well, there's many different reasons why you might mow your lawn. Your parents might tell you that you live in our house, you eat our food, so you're going to mow our lawn. Other parents will pay their kids to mow their lawn. Wow, isn't that novel? Other people will be like, well, the grass is long, let me go out and cut it. So there's all different kinds of motivations for cutting a lawn, from coercion to bribery to, well, let's just do it because that'll make it look better. In order for any change to occur, there needs to be a reason for it to happen. And all chemical reactions have a purpose, not a, predetermined purpose, like, what's the meaning of life, but some sort of thermodynamic reason to happen. Kind of like when I let go of a pen, it falls, not because that's what the universe dictates, but that's because that's what happens when you take two objects with mass and you let them do what two objects with mass naturally do. For redox reactions, the reason is a competition for electrons. One species wants electrons more than another species. And when I use the word wants, I'm not implying intent here. I'm basically anthropomorphizing the situation. One species has a greater affinity for electrons than another species, but wants kind of sums it up. So one species has a greater affinity for electrons than another species. We can actually use reference table J to figure out which elements these are. The more active metals are less likely to want to gain electrons, and ions of less reactive metals are more likely to want to gain electrons. For nonmetals, the higher up they are, the more active they are, the more likely they are going to be to gain electrons, and ions of the ones that are lower down are more likely to lose electrons. So one species will gain electrons that the other species loses. So if we're going to react potassium with sodium, for example, potassium will lose electrons to sodium ions, but sodium cannot lose electrons to potassium ions. All right. So here are the reaction types that result from this competition. We have synthesis, where two elements combine to make a compound. Again, this can also be called direct combination. So, for example, if potassium and bromine combine to form potassium bromide, that would be a perfect example of synthesis. Decomposition, which can be used to analyze the components of a substance, is when a compound is broken down into simpler substances. It can be all the way down to its constituent elements, but it doesn't necessarily have to be. And single replacement is when an element replaces one of the elements in the compound. If the element is a metal, it will replace the metal ion in the compound. If the element is a nonmetal, it will replace the nonmetal ion in the compound. In this case, the metal magnesium replaces hydrogen, and hydrogen is kicked off on its own. Okay, let's look at synthesis. In a synthesis reaction, two elements combine to make a compound. The elements in question have no charge. Why? Because the number of protons equals the number of electrons. Sodium has 11 protons and a configuration of 281, giving it 11 electrons. So a sodium atom has no ion charge. Similarly, chlorine has 17 protons and 17 electrons. But when they combine, the sodium will lose its valence electron to chlorine. The metal will lose the electron, the nonmetal will gain the electron, the metal will become positively charged, the nonmetal will become negatively charged. And the two oppositely charged ions will attract to form a new compound. Now, you might be tempted to write NaCl2. Don't do it. Look up the charges of the bonded ions and let that dictate your formula. And if the numbers don't work themselves out that way, then when you've got the completed reaction, just simply balance it. And this is an example of a synthesis reaction. Two elements combine to make a compound. There's one NaCl, there's the other NaCl. So two NAs plus Cl2 combines to form two NaCls. Okay, now what about the oxidation and reduction? Well, again, elements that are not part of a compound have no charge because they haven't gained or lost any electrons yet. So who is undergoing oxidation? Well, oxidation is a loss of electrons resulting in a more positive charge. Sodium becomes more positive. That means sodium lost the electron. Remember, electrons are negative, so if you lose something negative, you become positive. Yeah, that's just a secret between us. Okay. Now, that wasn't creepy at all. Okay. The chlorine, on the other hand, becomes more negative by gaining negative electrons. And so the sodium will give its electron to chlorine, meaning sodium will be oxidized and chlorine will be reduced. More specifically, Na0 will undergo oxidation and Cl2 will undergo reduction. That's synthesis. And just to give it a little bit of anthropomorphism once again, imagine that you take two separate people and they end up together. Marriage. Marriage is what brings us together here today. And that is synthesis. Decomposition is when a compound breaks back up into its original elements. So let's take a compound like water. We can decompose water into its original elements. Now, what elements is water going to break up into? What will A and B be? Well, one of the elements will be hydrogen, and the other element will be oxygen. Now, you may be tempted to write H2 plus O, but no. You would write H2, however, because hydrogen, when it's not in a compound, is a Brinkelhoff and is therefore diatomic. However, O is the O in Brinkelhoff, which means the oxygen will be diatomic as well. Now, don't fret that you don't have the same number of atoms of each element on both sides. We may have two O's on the left and only one on the I don't know my left from my right. Two O's on the right and only one on the left, but that's easy to fix. Just pop a 2 in front of the H2O. Sure, that unbalances the hydrogen, but that's easy to fix. And now we have a completed and balanced reaction, and this is what it looks like. We have two H2Os will break up to form two H2s and O2. Now, as far as the oxidation and reduction are concerned, again, remember that elements that are not in a compound have no charge, and elements in a compound have whatever charges allowed this drop and swap to happen. So the hydrogen and oxygen on the right side have no charge, but the hydrogen and oxygen in the water molecule do have oxidation states. Now, what's happening here? Hydrogen is going from +1 to 0. Hydrogen's charge is being reduced. Reduction is the gain of electrons. So H plus 1 is being reduced. O is going from -2 to 0. Its charge is becoming less negative and therefore more positive. Therefore, oxygen is losing electrons to hydrogen. And so O-2 undergoes oxidation and H plus 1 undergoes reduction. To anthropomorphize this, imagine we have a couple that decides to break up. Decomposition is similar to breaking up is hard to do. Now, single replacement. A plus BC forms AC plus B. All right, so we have potassium and zinc nitrate. So the formula works like this. The metal will replace the metal in the compound. So the metal will bond with the negative ion in solution, and the positive ion in solution will end up on its own. Potassium is going to go knock, 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 zinc. Get out of here. I'm bonding with nitrate. And the zinc's just like, what if I don't wanna? And the other metal will be, well, I'm more reactive than you are, so I'm giving you an ultimatum. And zinc's like, all right, I'll get out of here. Jeez. So the potassium ends up with the nitrate. There'll be a temptation to write KNO3 too. Don't do it, because K and NO3 may not give you charges that do that. And the zinc ends up on its own. Now, let's write the formula for our compound. K is +1, NO3 is -1. Ha, see? It was a good idea not to write KNO3 too, because the charges just don't support it. So how do we balance it? Well, we have two nitrates on the left, so make it two nitrates on the right. Two Ks on the right, let's make it two Ks on the left. This is balanced. Okay, this is what it looks like. We have two Ks and zinc nitrate. The Ks will take the zinc's place, and the zinc will go off by itself. So the K will bond with one NO3, the K will bond with the other NO3, and the poor zinc will end up single. Single replacement. Let's look at this from an oxidation and reduction standpoint. K by itself has no charge. Zinc has a +2 charge, nitrate has a -1 charge. So K is going from 0 to +1. It's becoming more positive by the loss of an electron. Who gains it? Zinc goes from +2 to 0. So zinc's charge is becoming more negative, and therefore zinc +2 is gaining the electron that the potassium lost. And therefore, the potassium 0 is what's oxidized, the zinc ion is reduced, and the nitrate ion doesn't change its charge at all. Being that it doesn't change its charge, that would be the spectator ion. If you think of reactions like a sport, the rules of the game dictate that electrons be lost or gained. So whoever is losing and gaining electrons is playing the game. If you're not playing the game, you're just watching it happen. You're a spectator to the whole thing. Therefore, since nitrate doesn't participate in the oxidation or reduction, it's a spectator ion. Now, this is a little bit more complicated than the previous two reactions, although it is a combination of both. In order for one to end up with the other, then somebody else has to get the boot. So, bye. Hello. So, there has to be a breakup before there can be a new relationship. That is single replacement. By the way, this particular thing was inspired by real events. The names will go unmentioned to protect the innocent. They are wonderful people, though. Your turn. Well, let's see what kind of reactions we have here. We have a compound that breaks up into two elements. What does that make this? Decomposition. Here we have aluminum replacing zinc. Therefore, it's single replacement. In this reaction, we combine two elements to make a compound. Therefore, it's synthesis. So you need to be able to recognize the reactions when you see them and identify what type they are. You also need to be able to identify who's oxidized, reduced, and which one is the spectator ion, if there is one. So first, write down the oxidation numbers, the charges of each species. Whichever one becomes more positive is oxidized, whichever becomes more negative is reduced, and whoever does not change charge will be the spectator. In this reaction, elements by themselves have no charge. N is +4, O is -2. Because 2 times -2 is -4, and so N has to be +4 to cancel that out. In this reaction, O goes from being -2 to 0. Its charge is becoming more positive. N is going from +4 to 0. Its charge is becoming more negative. So nitrogen is being reduced, where oxygen is being oxidized. Specifically, N+4 is being reduced, and N-2 is being oxidized. The zero charges is the end result once the reduction and oxidation have taken place. In this reaction, the aluminum on the left and the zinc on the right are not in compounds and therefore have no charge. The zinc in the compound has a charge of +2, the nitrate is -1. The aluminum in the compound is +3, the nitrate is -1. So aluminum is going from 0 to +3. Its charge is becoming more positive, and therefore aluminum 0 is oxidized. Zinc is going from +2 to 0, and therefore zinc +2 is being reduced. The nitrate remains -1, and therefore nitrate is the spectator ion. In this third reaction, iron and oxygen on the left have no charge since they're not part of a compound. But in a compound, iron is +3 and O is -2. The iron goes from 0 to +3. Going more positive is oxidation, so Fe0 undergoes oxidation. Oxygen goes from 0 to -2. And therefore, O0, or you could write O20, that would be acceptable, goes from 0 to -2, is reduced. And since there's no third ion here, there is no spectator ion. Finally, completing reactions. Look at the reactants and or products, whichever one you're given. What pattern do they fit? Place the missing elements where they belong on the other side according to the pattern. Use the charges of the elements to write proper formulas, and then balance the reaction. Here we're given reactants of potassium and oxygen. Two elements are combining. They'll form a compound. The compound will contain potassium and oxygen. On the periodic table, potassium has a +1 charge and oxygen has a -2 charge. Therefore, drop and swap will give us a formula of K2O. We always balance it after we've done this. So we have 2 Ks on the left, so we'll put 2 Ks on the other side. We have 1 O on the right, so we'll put a 2 in front there. But that makes the Ks 4, so we change that 2 to a 4. The other option is to balance the oxygen first. We have 2 on the left, we had 1 on the right. By putting a 2 in front, we balance oxygen. 2 times 2 is 4, so we can put a 4 for potassium. So balancing oxygen first would actually help us avoid having to make our revision. In this reaction, we end up with lithium sulfate plus aluminum. This follows the pattern of single replacement. Aluminum used to be bonded to sulfate. Lithium used to be by itself. So lithium was by itself and aluminum was with sulfate. Aluminum's charge is +3, sulfate's is -2. You can look this up. And by dropping and swapping, we can complete the formula. To balance it, we have 1 aluminum on the left and 2 on the right, so we can put a 2 in front of lithium. We have 2 aluminum on the left, and we have 1 on the right, so we put a 2 in front of aluminum. We have 3 sulfates on the left. We only have 1 on the right, so we put a 3 in front. But this changes lithium from 2 to 3 times 2 is 6, so we put a 6 in front of lithium on the left. And now we have a completed and balanced reaction. Final example, copper oxide and an arrow. Well, you start with a compound, therefore it's decomposition. The copper oxide will decompose into the elements it's made of. But you can't just stop there. Oxygen is diatomic. It's Brinkelhoff. Therefore, we must put a 2 after it and then balance accordingly. And that is how you complete reactions. That's a lot to digest, and I recommend you do lots of practice at this. Once you've done a lot of practice, you're going to find yourself getting really good at this. So go ahead and do what you got to do, and I will see you next time. For a second, I was wondering if I was even recording this. Turns out, yes, I'm recording this, except now I'm not going to record this because I'm going to say